Hello, my name is Ben and I'm going to walk you through my Arduino Smart Lock system for SIT 111 Task 3.8 High Distinction. This task is a fully functional smart lock controlled via Linux command line serial commands featuring a servo-controlled lock, PIR motion detection, an OLED display, a 4-button keypad, and advanced features like auto lock, security lockout, and event logging. The goal was to create a creative, reliable system that integrates Arduino with Linux, meeting the high distinction criteria with robust things like robust functionality and clear documentation, all of that. In this screen task, I'll show the hardware setup, break down the Arduino code line by line, demonstrate Linux command integration, and highlight how it all comes together. So let's dive in, starting just with the hardware setup that I've got here. The Arduino Uno is the brain of the system, running our sketch. The servo motor controls the lock mechanism, moving between 0 degrees, which is locked, and 90 degrees, which is unlocked. The PIR motion sensor detects motion for security alerts, connected to pin 2. The OLED display shows system status, pin entry, and alerts via I2C communication. And the buzzer provides audible feedback for actions like motion detection or pin errors on pin 8. And the green LEDs indicate lock status, so it's green for unlocked and red for locked on pins 3 and 4. The push buttons, there's 4 of them, they form a keypad on pins 5, 6 and 7 and 10 using internal pull-up resistors. And with jumper wires and resistors, they just connect everything securely. This setup is pretty robust, and it definitely meets the assignment's requirements for physical, this setup meets the assignment's requirements for physical hardware, with extra features like the OLED and keypad for, hopefully, a high distinction score. But yeah, let's move on to the code now. I'll open that here. Which is about 800 lines long-ish. So it took a while to do, but it's long, but it's well organized with lots and lots of comments, as you can clearly see. And I'll explain what each section does, and why it's included to meet the assignment's goals. And at the top, we include the external libraries: the servo motor for lock mechanism, wire for I2C communication with the OLED, and then Adafruit GFX and Adafruit SSD1306 for the display. I've got EEPROM for persistent settings storage and Avra WDT for the watchdog timer to ensure system reliability. I'll get to that later though. The comment block consists of servo motor lock, PIR detection, OLED interface, keypad, serial commands, EEPROM storage, auto lock, security lockout, event logging, and watchdog protection. So this definitely shows the project's complexity and hopefully creativity as well. And yeah, so moving down to the PIR display. Here we go. The pin definitions assign... Actually, let's go up here and go through the pin definitions first. The pin definitions assign hardware to specific pins, like servo _pin to pin 9 for the servo, PIR pin 2 for the motion detection, buzzer for 8 for alerts, etc. and so on. I define the servo positions, so we can see locked is 0 degrees, unlocked is 90 degrees, and then the EEPROM addresses store the pin auto lock delay, alarm settings, and an initialization flag to persist settings across power cycles. And these constants make the code modular and easy to adjust, definitely aligning with the assignment's focus on quality documentation. It looks about as... It took ages. But yeah, let's move on to the pin management system. The pin system uses default pin 1, 2, 3, 4. Over here, and it is stored in Promgram to save RAM, which is very precious. It's a critical optimization for the Uno's limited memory. Correct pin holds the current pin, and entered pin stores the user's input for keypad. Debouncing, which is debounce delay equals 200 milliseconds, prevents multiple button presses, ensuring a reliable input. And the system supports secure pin entry persistence, which is, I think, a pretty creative feature for in the name of user interaction. The system state and security features. These are pretty cool. The state variables track the lock, so is locked in the motion detected, which is PIR state and last motion time. Auto lock, which is auto lock delay, last unlock time. These are the security lockout. These are the state variables that track the lock and motion detection. And the security lockout activates after 3 failed pin attempts, locking the system for 30 seconds, adding, I think, a robust security layer. And then the non-blocking buzzer system provides feedback without halting the program, so it shows careful design and responsiveness too. Then we come to event logging and statistics. The event struct logs up to 5 events. I'd prefer it to be, 20, 50, 100 events for it to be a bit more practical, but this isn't too bad either. And it does so in a circular buffer with timestamps and type/detail codes to save on memory, which again is like so precious. We've got counters as well, so motion count, unlock count, failed attempts. It tracks the system's activity, which is accessible via a serial command, which I'll get to later. And the logging system is another very practical addition of providing insights into system behavior for debugging and presentation. Unfortunately, this became less useful as the integration of this was added kind of very late, but again, troubleshooting was ongoing all throughout the setup. Speaking of, let's go to the setup functions. The setup function initializes the system. So it enables the watchdog timer with WDT_enable 8 seconds to reset the Arduino if it hangs, ensuring reliability. Serial communication starts at 9600 baud for Linux commands and debugging. And then the pins are configured, so inputs for PIR and buttons with pull-ups, outputs for LEDs and buzzer. The servo attaches to pin 9 and sets to the locked position, and the load settings from EEPROM retrieves the pin, auto lock delay and alarm settings, initializing defaults if EEPROM is initialized. So I've covered all the bases, or as much as I can anyway. Scroll down a bit more. The PIR sensor calibrates for 3 seconds to stabilize, and the OLED initializes with fallback if it fails. The OLED initialization failed a lot, specifically I think due to memory, which I'll detail further soon. And then the LEDs update, and a startup event is logged, and the system prints its status and available commands ready for Linux interaction, which is cool stuff. But yeah, that's all out here. So it's locked, unlocked, fail, okay, calibrated, uncalibrated, and ready. Now we'll look at the main loop. And the loop function runs continuously, which resets the watchdog timer to prevent crashes. It monitors system health every 10 seconds, printing the PIR and lock status for debugging, which did eventually help. The non-blocking tasks, which are pretty cool, include handle buzzer, which turns off the buzzer after its duration, handle security lockout, which ends the lockout after 30 seconds, and handle auto lock, locks the door if the auto lock timer expires. The serial commands are processed via handle serial command when data is available. And the PIR motion sensor triggers alerts and logs events with a 5-second cooldown to prevent spam. And then the keypad buttons are checked with debouncing, and the OLED updates to show pin entry for lockout status, which I'll show in the physical setup later on. I've also got a 50-second delay that balances responsiveness with CPU usage. This is kind of overdoing it at this point. I don't need the 50-second delay, it's just like good practice. But yeah, now we'll move on to the key functions, and this is mostly the cool stuff, really. We'll start at the top with the PIR calibration. It waits 3 seconds for PIR sensor to stabilize, displaying progress on the OLED, and this this just ensures reliable motion detection, because when it starts up it has false positives, which is not what I want. So this was necessary. Then we look at EEPROM management. Load settings from EEPROM and save settings from EEPROM. They handle persistent storage of the pin, auto lock, delay, and alarm settings, which validates data to prevent errors. Also good practice, but also just probably one of my most favorite additions. I had no idea this existed, and it was worth my time. And then the serial command processing. This is also important. It phases commands like lock, unlock, status, stats, set, pin as well, all of them, and help too. I made a help command. And it validates the inputs like their 4-digit pin entry and updates EEPROM, showing robust Linux integration. I was thinking about this from the start. It needed to be planned well and truly. The lock control, let's scroll down a bit. Lock control, this moves the server, updates the LEDs, display and buzzer, and logs events. These ensure reliable physical operation. The display management, which is update display with the timeout. I think we're a little bit ahead here. This is the serial command. This is saving the alarm settings, event logging. That's okay. Let's go back up here. I'll just talk about the keypad processing briefly. It handles pin entry with debouncing. Again, it just validates the correct pin and triggers unlock or lockout. It's a key user interaction feature. Now we'll look at the command Linux command integration, which is all the way down here. This is the event logging with helper functions. So it prints human readable event type for single character codes. The single character codes, these were also intentional. It saves on memory, which is like really limited with the Arduino Uno. We'll scroll down a bit further. This is the non-blocking buzzer control I talked about. These are the lock control functions. So again, it physically locks the door, updates all related stats. And then the unlock door, the LED indicators, display management functions. This is for the OLED. This one updates the set timeout to return the pin entry, and this is the set timeout timer. This is all for the OLED again. There was a lot of work that went into the OLED display, and this was also another really important addition. And this is mostly just displaying the key stats and states. So security lockout or waiting, how many seconds it has left to unlock. It shows the normal pin entry, which I'll show again in the much later stage. And it displays the pin progress too, which is good for user interaction. It just looks good. And I added a system reset function. This became pretty important. I implemented this at the very beginning. This was one of the first commands I integrated because it was useful to set everything back to 0. So I defined all the different states and set them up, and then this was the first one I set up so that I could just start from a clean slate every time I try and troubleshoot something. So very useful. And it resets and calibrates the sensor, it clears the logs, gets rid of all the garbage, and then we have the keypad input processing. And we check the buttons, again, a debounce check, ignores buttons when they are within a debounce period. And then we add the digits to the pin buffer with bounds checking, good practice. Update the display to show progress, again with the OLED I was talking about, just for good user interaction. Talks about the pin correct, pin incorrect, and we've got comments about the maximum fails reached, which is set at 3 at the moment. And then of course at the bottom we've got the reset pin thing. But yeah, it's pretty cool. The Linux command integration can come much later. But yeah, that's really cool. One challenge was the OLED initialization failures that I talked about. So I added display available to ensure the system works without it, showing resilience. The EEPROM validation was tricky as well since it corrupted pins and could lock out the system, which was not fun, hence the reset function I talked about. So I also added checks to reset the defaults if it's invalid. The watchdog timer was definitely critical to prevent system hangs during long-running tests. It was very rarely useful, I'll admit, but I think it was good practice to implement, and I learned a lot by putting it in as well. I learned a lot about serial communication as well, and definitely above all was memory optimization, using EEPROM for example, and non-blocking programming for responsiveness. This was a mighty effort, especially with memory optimization. It's like the bane of my existence with this project, but it's good. It's very well optimized. I think if I added any more features that I wanted to, like a temperature monitor or something, it would just crash the system. There was no more room for it. But yeah, that's my Arduino Smart Lock system, and it definitely meets the SRT 111 Task 3.HD requirements with creative, reliable design controlled via Linux commands, which is I'll talk about next. The servo lock, PIR sensor, OLED keypad, and advanced features, again like auto lock, etc., push it beyond the basic requirements for a high distinction score. But yeah, let's move on to the Linux integration. Okay, in this section I'll walk you through a bash script I wrote to control the Arduino Uno via serial communication on Kali Linux, showcasing robust integration, user-friendly features, and reliability. The script offers an interactive menu, automated demos, security testing, and system monitoring, which meet the assignment's goals of creativity and effective Arduino Linux interaction. I'll break down the code, break down the script's code, demonstrate it in action, and explain how it enhances the project. So yeah, let's get started. I'll start at the top, which is, it's about 300 lines long, and it's pretty well commented. There's a few more pieces, definitely a few more pieces that I'd like to comment, but it's not that bad. It makes good sense. I'll explain it all. We'll start at the top with the script header and configuration. The script starts with shebang to run in bash and a comment block describing its purpose, which is just controlling the Arduino Smart Lock via serial communication. The configuration variables define the serial port, which is in my case TTY ACM0, baud rate 9600, and timeout, which is 3 for serial communication, matching Arduino's 9600 baud rate. These settings are customizable, so you can make the script adaptable to different setups, which align with, good practice, flexibility, and so on. The device permissions check that comes down here. This was also thinking about other people using this script. So the check_device function verifies the Arduino is connected at, in my case, TTY ACM0 using -e $device. If the device isn't found, it lists available UCM/ACM devices with ls-la dev TTY with a wildcard. And then it greps all of them with a USB through to ACM, and suggests troubleshooting setups as well, like ls USB and dmessage tail, which ensure reliability, and they're very helpful. I think I've tested this multiple times and it's pretty neat. Actually, I'm proud of this. The check_permissions function checks, pretty self-explanatory. It just checks read/write access to the serial port with $device -w $device. If permissions are lacking, it attempts to fix them with sudo gmod 666 device, or advises adding the user to the dial-out group, which is necessary for this. These checks prevent runtime errors as well, which is good. So it's robust integration. And then let's look at the send commands function. This one's pretty important. In fact, it's like the main thing. The send_command function is the core of the Arduino communication. It takes a command like lock or unlock, and description prints the command in purple and clears the serial buffer with timeout 0.1 cat device to device null to avoid stale data. The command is sent with printf which is $$S/N $command to the device, which ensure a new line for Arduino's phaser or parser. Anyway, a 3-second sleep accounts for Arduino's processing time, and a 5-second timeout reads the response with timeout 5 cat device. This was really important. Otherwise, it just didn't grant Arduino enough time to respond. Responses are printed in cyan with a warning showing if no response is received, demonstrating reliable communication and error handling, which I also thought about. I'll run through each of the menu options now, starting with the interactive mode. The interactive mode function creates a command line interface with a prompt Arduino. It lists available commands for you, like lock, unlock status, and reads user input in a loop using read-r user_input, which is simple and straightforward. The case statement handles quit/exit to exit or send other inputs to send_command, allowing flexible manual control. This mode makes the script user-friendly, which enhances the assignment's focus on effective integration. The demo sequence, which I'm going to show you very soon, this runs, I'll run the run_demo function, which automates a sequence of commands to showcase the system, which will speed up this significantly. It sends commands like help status, unlock, lock, set pin to 4321, auto lock to alarm_off, alarm_on, and get logs. It tries all of them. It also resets the settings with decent outputs as well. The sleeps, I should mention these two as well. Ensure Arduino processes each command, and the sequence demonstrates all the features, making it ideal for this presentation. The security test, this was an unnecessary sort of implementation. It was more just my desire to tick as many boxes as possible. But it's useful for checking that the user's Arduino code lines up with the script as well. The run_security test function tests error handling, which is the main focus. So it sends invalid commands like status lock valid commands first, like status and lock, and then invalid ones like set pin to 9999. I used to have options where you could set the pin to 9999 or 8234, but you can't do that with a physical setup. So I've now limited it to the digits 1, 2, 3, 4. Other invalid ones like lockout for 500, like you can only do that for 255 minutes max, or just an invalid command. And these trigger Arduino's validation. It checks logs and stats to show security features like failed attempt tracking, and that complements the Arduino's lockout system. So this highlights the system's robustness, which is a key high distinction criteria, I think. Next bit is the system monitoring. This one's pretty short. It just, this monitor_system function runs a loop checking system status every 10 seconds with a timestamp or date. It's interruptible with Control-C, which breaks the script. I've been trying to think of alternative ways rather than breaking the script entirely, but anyway, it makes it useful for real-time monitoring during testing or demos. Again, this was a pretty late integration since I basically made the script when everything else was done, but it's still a cool addition, and it adds a practical feature for continuous operation, which shows creativity. Next is the menu. This is what it looks like. I'll show you again soon. The display_banner function prints the styled headers for visual appeal. The display_menu function shows 8 menu options like quick status, interactive mode, running the demo, which I'll show soon, and for user navigation as well. The device_info function displays the device path, baud rate, permissions, and tests connectivity with a help command. The main function ties everything together. So it runs, running checks, waiting for Arduino initialization, which is sleep 3, and looping the menu with read-r choice and a case statement. The trap handles Control-C for clean exits, enhancing reliability as well. This was quite a complex part. This didn't happen overnight. This was lots and lots of trial and error and research and looking at GitHub and all of that stuff. But yeah, again, Control C for clean exit. And then the root check from execution, this is just the script checking if it's as root and warns against it if it's for security, which is cool. And then the main function, of course, is called at the start of the script to ensuring all checks and menu options are accessible, which is excellent. Now I'm going to exit out of this and we'll run the code. // like so. It'll initialize, talk to my Arduino, and you get your options offered here. I'm going to select the top one, or number 3, just for the demonstration. Enter 3 here. It's going to start running the smart lock demo sequence. So the first one it's sending is the help command, where it displays the available commands. And here they all are. First of all, the system initialization starts, of course, so calibrates the PRI sensor, pins configured, attaching the servo. Status, checking the system startup. Not sure if this is right actually. Help, checking the status, calibrating pin sensor for a 3rd time. Yeah, this isn't right. I'll circle back to you.
One eternity later.
Okay, I ran into some problems with serial communications, garbled responses and unexpected Arduino resets, which disrupted the command execution. I fixed it by improving the command execution and the bash script in general, and I'll explain what went wrong, how I resolved it, and why it matters, because this is like a perfect opportunity to run through exactly what that was. I did a lot. This took a day and a half to fix, but it's okay. So yeah, let's jump into the troubleshooting process. The problem I identified was, while testing the bash script, I noticed 3 issues. 1, the device or resource was busy, so something was locking the serial port. 2 was fragmented text like ROM equals or PRI sensor activating or whatever. Just responses were garbled and mixed up start messages with commands. It was like the Arduino was restarted every time I sent a command, which obviously disrupts communication. And the root cause of this was opening and closing the serial port with dev tty acm0 for each command, with like echo command to the port and cat command to the point, was the issue. The Arduino's auto reset feature triggered a reset on each connection via the DTR line, and startup messages, which are 6 to 7 seconds, take 6 to 7 seconds sometimes, including PRI calibration, contaminated the responses. So I'll walk through the I'll walk through the fixes that I implemented. I made 5 key changes to the bash script to ensure reliable communication. The first thing I updated was the send command function, which is just here now. First thing is the persistent connection. Instead of reopening a port, I used exec3 to the device to open it once, send commands with the echo command to the arrow and 3, and close it with exec3 arrow and then that prevents the DTR resets, which is exactly what I need. The extended wait increased for the initialization from 3 seconds to 12 seconds. So sleep 12 to cover the Arduino startup, which, given it's heavy on the memory at the moment, is what it needs. The next bit is the buffer clearing. So I added a loop to read and discard startup messages before sending commands, because that was a consistent issue. It would like startup commands every time I sent a command. So using while ifs equals read -t1 -u3, this keeps the responses clean. So we've got the persistent functions, we've got the send commands via persistent connection, got some if else to make sure it's reliable, sends it via a new line, again using arrow and 3. I'll wait for Arduino to process it. It collects the responses with a timeout, and then we have the while loop here. which is exactly what I need. And then we start getting into interactive mode and the rest of my functions, which have all sort of been modified each in their little only way. I've got connection tracking as well. I added a connection_open flag to prevent multiple port opens, ensuring no resource conflicts. These changes mimic probably more professional serial terminals like Screen, which maintain a stable session as opposed to my previously slightly janky setup. But I'll just talk about the impact too. So seeing the fix in action, if I started the command again and went through each command, actually, you know what, I'll do that now. Let's just continue with the setup. We'll go, let's go /Arduino, and here we go. We'll do the full scan again to go through the entire, all of my commands. So again, it waits for the Arduino to complete initialization. I asked for the password because it requires the permissions to keep the port open. It clears the initialization from the data buffer. Persistent connection is established. Arduino starts responding to the commands. It runs the lock sequence demonstration, and here we can see it starts coming through. So the first command it sends is help, and the response is all the different commands you can set. The status tells you whether it's locked, the alarm is on, the sensitivity of the motion sensor, whether it's calibrated or not, tells you the loop it's on as well. I think this would be the next thing to get rid of, is it's still looping through the diagnoses and stuff, which isn't exactly what I need when I'm trying to show off the commands. It locks and unlocks the door. It just did that in front of me. I'll demonstrate that in the physical in the next section. It sets the auto lock, so it's going to lock after 2 minutes. I can change this. Changes the motion alarm off or on, and then it gets locked. So in this case, it's been locked. You can see all the commands that have gone through. It set the pin. It auto-enabled the lock. Motion sensor was disabled and enabled. We set the command to 1, 2, 3, 4. We change the auto lock back to 0, and then it completes the sequence. And there you have it. It's cool stuff. I'll show the device information as well. As you can see, it's ACM0. The baud rate is 9600, which sees the permissions. This is the kind of script that'll be useful for someone using their setup. It does all the work for them, which is very nice. Again, with all of these commands, I check the connection to make sure it's stable and safe and working before anything else. And then, only then, does it close. So I absolutely will not run into this issue again. And this definitely taught me that serial communication with Arduino requires session management, not like file-like I/O. So the DTR reset was a hardware quirk that I hadn't anticipated. The solution was persistent connections and proper timing, which made the system more robust, which obviously aligned on the assignments focused on reliability, troubleshooting, etc. And this fix polished my demonstration, ensuring a professional presentation. And I'll move on to the next part of my presentation, which is showing the screen setup as well. Okay, in this segment of the task, I'll demonstrate how Screen provides the simple terminal-based way to send commands to the smart lock system as per the assignment suggests. This highlights the basic integration without the custom script that I made, proving the Arduino's responsiveness and my understanding of serial tools. I'll cover the setup, basic usage, and a little demo. As you can see, we've got it going up here. My Arduino is plugged in and the sketch is uploaded, and the system runs at 9600 baud as defined in the code. But yeah, we're set up and we're running and we're good and ready to go. So I've got the basic commands over here that I can copy and paste. So for example, if I test stats, and if I copy and paste it down here, you can see the commands, it's detected motion once, its uptime has been 102 seconds, 107 seconds, which is just what we want. I can also try and enter the code. I'm doing that now. 1, 2, 3, 4. and it unlocks. And then we can do status, copy and paste that. And then it tells you it's unlocked. And it tells you, of course, the status of everything else. We can try getting help. Copy and paste that down here. It tells you all the commands: lock, unlock, status, stats, reset, and so on. You can set the pin. We can do get logs. Copy and paste that as well. Here we go. So start's been ready for 4 seconds. Motion has been locked for 104. Unlock menu has been 120. It's just what's most recently happened, basically. I would like this to be much longer, but because of memory restraints, again, it's not exactly possible. We'll copy lock and we'll paste it down here as well. The door just got unlocked, it tells you here. And yeah, that's pretty cool. I'm going to show you the physical setup very soon, but that'll show all of this in more detail, but this about sums it up. Common issues I had with this was the wrong port. So I needed to use dmessage permissions to add myself to the dial-out group, and then log in and log out again. There was also a brief board mismatch which caused like garbage output. For longer sessions, the screen is better for raw cat or echo for bidirectional chat. And one insight, I guess, is that using screen during development helped me to debug timing issues, like the 3-second sleep issue in my bash script. It's definitely a fundamental tool for microcontroller interfacing, and it's directly tied to the assignment's learning objectives, which is great. But there you have it. That's screen in action, providing the direct no-frills control over the Arduino SmartLock system via Linux serial commands. Combined with the bash script, this shows a spectrum of integration options, from basic tools to custom automation, all of which are reliable and now quite responsive. But yeah, that completes the command line demonstration for the project. And next up is the physical demonstration.